I'm not sure what rank exactly they gave me, but I want to begin with a quick introduction of some things you probably don't know about me. So I'm dad of 3 daughters, which is, in general, pretty great. Does it actually work? Guess not. Oh, that would be good. So I'm a dad of 3 daughters, which in general is pretty awesome, but it also gives me the additional excuse of doing things like that and pretending it's for my daughters. I have a lot of PHP elephants. I'm an amateur photographer, and I'm pretty crazy about that, and this is kind of my standard travel gear. I'm crazy about spicy food. It's not that I like it. I'm really crazy about it. It's probably some sort of a mental illness level. So if you're into that, I encourage you to challenge me. And I've been coding since the age of 12, starting with GW Basic. If anyone here is familiar with that. But we're not here to talk about me today. We're here to talk about PHP. And I wanted to touch 2 main topics today. One is the evolution of major versions of PHP, a bit about the past, and more about the present and future, focus on PHP 7 and also about things to come. And then I also want to talk about the architecture of how PHP is being deployed. So not so much, on the second part, not so much about how PHP itself is built, what the language looks like, but actually how it fits into the bigger picture with the components that are surrounding it, primarily the web server. So I want to begin with PHP 3. That's the level of resolution that we had back then. PHP 3 is the first version that I was involved with, and the main capabilities it had, I think the main features were that it was the first time that PHP was really a full-fledged language, with many of the characteristics that we still have in PHP 7 and we'll even have in PHP 8, in terms of how expressions work, how functions work, and things like that. That was the first version that kind of resembles PHP of today. And the second thing, which arguably was probably even more important, or at least equally important, is the fact that it was extensible. It was very easy to add features, to add support for new databases, for new protocols, and so on, without having to have knowledge of compilers, of the interpreter itself. You still needed to be a C developer, and a fairly good one at that, but it became a lot more accessible compared to the predecessor. PHP 3, however, was pretty bad overall. I mean, it became ridiculously popular, but it was pretty badly designed when it comes to performance. So it's not that it wasn't sophisticated. In fact, it was extremely sophisticated, but it was really implemented the wrong way. So we needed quite a bit of sophistication to kind of make it work. But at the end of the day, it was kind of like a horse and carriage in terms of performance. Anyone here ever used PHP 3? Okay, we have a few. So if you remember back in the days, we were saying things like, it's optimized for small applications, for simple applications. The reality it wasn't. It was just slow. So that was kind of a way to get away with it and kind of pretend as if it's kind of by design. It's not. It wasn't. And PHP 4 came to solve that issue, and for the first time it had reasonable performance, so you could actually develop some real-world apps on top of it and actually deploy them without having your users shout at you. The second thing that PHP 4 had going for it is that the language implementation itself was very modular, a lot more modular than PHP 3, and to a large degree, in terms of the high-level components, they're the same components that exist today, even in PHP 7 and PHP 8 to come. So in terms of the compiler, the executor, things like opcache, and so on, those are things that were all designed as a part of the PHP 4 initiative. And last but not least, it was the first version that also had the capability that introduced the ability to have language plugins. So things like opcache, but not just, things like debuggers, like Xdebugger and others, and APM modules, plugins that plug into the brain of the language and either change or augment it to do additional things. That was done, that was introduced in PHP 4, and I think it was a very important milestone. You can see, by the way, that the resolution is getting better with every version. So this was PHP 4, and that's already PHP 5. So we got to the kind of reasonable resolution at the time. And PHP 5 had really one thing going for it, one major thing going for it. It had a revamped object model. So the object model of PHP existed, I believe, since 3, but it was done as an afterthought, at best. When people were beginning to try and implement all sorts of frameworks on top of PHP, the shortcomings of the object model were very apparent. And I think it was the main, perhaps the only time where we decided to intentionally break compatibility in a fairly big way in order to improve the syntax of the language, the semantics of the language. And we changed the object model to be a lot more like that of Java. Now, PHP 5 was actually a bit slower than PHP 4 in most cases. So, performance, even though performance was always dear to our hearts, PHP 5 was actually a small step in the wrong direction. But after 5.0 was released and we got the object model correct, more or less, we started investing heavily again in improving performance. And with every version that came out, starting with 5.1 and 5.2 and 5.3 and 5.4, we improved performance substantially with every release. It was evolutionary. It wasn't like the transition from PHP 3 to 4, but it was quite substantial. And at some point, probably around PHP 5.5, maybe even 5.4, I don't remember exactly, we started hitting a plateau. It was very difficult to squeeze more performance out of this implementation. And despite efforts, and back then it could be years in between versions, and despite a lot of efforts of trying to optimize all sorts of elements in PHP, in practice we managed to get somewhere between 2 to 5% gains on synthetic benchmarks, which usually translated to pretty much nothing in real-world performance. And we realized that if we wanted to keep on improving the performance of PHP, we would have to go in a different direction. The direction that seemed to make the most sense was JIT. JIT stands for just-in-time or just-in-time compilation. And it's a strategy to improve the performance of dynamic languages that, by the way, all of you are using. Any of you using a browser, which means pretty much everyone, is using JIT, because all of the browsers today, be them on desktop or mobile, are using this strategy to improve performance. It wouldn't be possible to have the complex applications, the complex JavaScript applications that we have today, like things like spreadsheets and mapping solutions in the browser, if it wasn't for JIT. And what JIT does at a very high level is essentially when you have a dynamic language, the way it usually works is that the language takes the source code that you've developed and translates or compiles it into some sort of an intermediate representation, and then it feeds it to the interpreter, which kind of iterates over it and interprets it, executes it. What JIT does is take the intermediate code and the parts of it which are detected too infrequently are actually translated all the way down to machine code, to assembly. And that can improve performance quite a bit, depending on the workload, but instead of having the interpreter, some sort of a program run in memory and interpret the intermediate code kind of line by line, you actually translate it all the way down to machine code that you can just send to the CPU and execute directly. And again, It's a strategy, it's a proven strategy that worked really well for things like JavaScript, and we thought that this is kind of the natural next step of the performance evolution of PHP. And we started working on it probably around 2012, and within a few months we had a very early prototype that could run the synthetic benchmark of PHP, bench.php. It's a part of the PHP distribution if you want to take a look. And the results were actually quite good. I don't know if you can see at the back, but essentially you have here a table of all the different tests that are being conducted by the synthetic benchmark. And on average, the JIT version was somewhere between 5 and 6 times faster than the non-JITted version. So that's something that made us very optimistic, and it was actually, kind of beyond our expectations at that point. So we were very energized and continued to work on the prototype to get it to do some things, kind of beyond bench.php, because at the end of the day, you don't run bench.php all day. And we kind of improved the prototype and made it work with more and more elements of PHP, and at some point we were able to run WordPress on it. And when we ran WordPress on it, it was a bit more of this kind of phase, because we didn't measure any performance difference at all. Sometimes you probably know this feeling from, not necessarily just performance, but you're working on something, the first time you try it doesn't work, no big deal. You tinker with it until it works. So that's what we did. We tinkered with it, and we tried to understand why is it that, where's the bug, where's the issue that it prevents WordPress from, becoming faster like our synthetic benchmark did. But after about a year of tinkering with it, we came to the conclusion that it just wasn't being, the current strategy of JIT was just not yielding the kind of performance gains, or for that matter, any performance gains that we were looking for. In fact, in some cases, it was somewhere between 2 to 5% slower. So that was really disappointing. After a year of thinking about it ourselves, we also started working with folks from Intel, trying to help us trace and kind of figure that out, because it was really weird. It's uncommon. We're used to synthetic benchmarks being better than real-world benchmarks, but the discrepancy between 6 times better performance on synthetic and 0 to -5% on real-world, that's something we never bumped into. And at some point, we came up with a theory together that the source of the bottleneck that was preventing us from realizing the performance gains had to do with the fact that PHP was kind of fat from a memory utilization point of view. It was just using too much memory. The relationship between memory usage and performance is a very important one. It has a lot of different elements to it. Okay. A lot of different elements to it. And specifically in our case, we thought it had to do with a capability of the CPU, something pretty low level, which is called on-chip caching. So all of the CPUs, again, whether they're on your mobile device or on your computers, have cache memory inside the chip itself. Now, we're talking about very small amounts of memory. So if your computer has, 16 or 8 or 32 or whatever gigabytes of memory, when we're talking about on-chip cache, we're talking about not gigabytes, but not even megabytes. We're talking about typically kilobytes, at the level of hundreds of kilobytes. A very small amount of memory, which is very, very fast. And it's a lot faster to go to the on-chip cache compared to going to main memory. So we're used to memory being fast compared to disk, but when we compare memory, the main memory, to the on-chip cache, it's dead slow. And the theory, going back to JIT, the theory was that because PHP was kind of not very efficient in terms of its memory utilization, we had a lot of cache misses for the CPU. And the CPU would have to go back to the main memory and obtain the piece of memory that it needed a lot more frequently than it should. And that was effectively the reason why there was a bottleneck and it wasn't showing us any sort of performance gains. So we decided to go on a diet. Well, not exactly this kind of diet, not fruits and vegetables involved, but we went on a memory utilization diet, and we tried to reduce the size of the key data structures of PHP. Does that work? No. So basically, at the top, you see the Zeev. The Zeev is kind of the basic building block of PHP. It's the basic data structures that hold any kind of value, whether it's an integer, or a string, or an object, and so on. And we managed to trim it down from 24 bytes to 16, which 24 and 16, bytes, it's nothing. But when you multiply it by potentially thousands and sometimes even hundreds of thousands of different Zeevs you could have in a single request, that actually becomes quite a lot. And especially if you factor in the fact that you're moving these Zeevs back and forth between functions all the time. The difference here, obviously in percentage, it's a third off. So the difference is actually huge. Out of all these 3 reductions, actually the moderate 8-byte reduction from 24 to 16 on this building block was probably the most important one. But the other data structures also went on a diet. Bucket is a data structure that is used to hold a value inside a symbol table or an array. And a hash table is the data structure that holds the symbol table itself or the array itself. So all of them went on substantial diets. And again, to remind you the context, the goal was to get rid of the bottleneck that we thought was preventing JIT from realizing its potential. One thing I didn't mention is that when we did this diet, we actually had to throw away, or at least put aside, all of the work we've done on JIT. It wasn't really practical to make this change on top of the JITted version that we've developed, on top of the JIT prototype. So actually threw it away. We started from scratch using the PHP 5.5 code base and put it through this diet. And then, in order to make sure that everything works, we ran all sorts of applications on top of the prototype. And to our surprise, when we benchmarked it, we saw that the performance actually improved quite a bit. So we're kind of happy faces again. We weren't expecting it. We were expecting JIT to give us a performance boost, which it didn't. We were not expecting this reduction in memory utilization to give us a performance boost, but it actually gave us a performance boost of about 35%, but on real-world apps, not on synthetic benchmarks. 35% on real-world apps just by changing the language version. That is huge, something that we never managed to do ever since PHP 3 to 4. At that point, we figured that it probably wouldn't make sense to wait a few more years until we have re-implemented JIT on top of this new thin version of PHP. And we decided to make it available, and it became the basis for PHP 7. And by the time PHP 7 was released, already a few years ago, essentially we managed to make it go through additional optimization and an additional reduction in data structure size, which made PHP 7, as I'm sure you all know, roughly twice as fast compared to PHP 5. And again, this is not the standard marketing that you often hear, up to, 20% or up to 5 times faster, and in practice you measure like 2%. In PHP 7, as again, I'm sure many of you know, the performance gains are very tangible and they're very real world, and moving from workloads that were running on PHP 5.6 to PHP 7.0 will actually, in the vast majority of cases, make it either go twice as fast or allow you to half the amount of hardware that you're using, and sometimes kind of a bit of both. After PHP 7 was released, pretty much immediately, once we were done with this project, we decided to go back to JIT, because if you remember, that was kind of the original point behind this diet. And we thought, now it would be time to see if it actually did the trick, and whether JIT in PHP would, now that the data structures are thinner, would actually bring us some real-world performance gains. So before I answer this question, I want to quickly show you a benchmark that compares PHP 7 to PHP 8. Well, I should say something about that. PHP 8 is obviously not yet out, but a piece of good news is that JIT has been accepted, has been voted on, and has been accepted, and will be a part of PHP 8. So we can kind of say that the thing on the right is a PHP 8 prototype. And let's just go with the benchmarks. On the left-hand side, we're seeing PHP 7. It's rendering factors in real time, something that I'm sure all of you do all the time. And on the right-hand side, we have the prototype of PHP 8 doing the same thing. So even visually, you can see that the right-hand side is way faster. It's actually done with the benchmark already, even though PHP 7 started ahead of time. And you can see, hopefully you can see the frames per second on PHP 7 are 8.5 frames per second, on PHP 8, the 19.5. So it's more than twice as fast on this benchmark compared to 7. So that's the good news. The good news, again, accepted into PHP 8, it's really faster. The bad news is that we still didn't manage to solve the mystery of why we're not seeing performance gains on real-world apps. And in most real-world apps that we've tested on, the performance gains from JIT, they're better than they used to be, but they're still kind of hovering between 0 and 5%. So why did we accept JIT into PHP 8 if it's not bringing us tangible gains in performance in real-world apps? There's several reasons for that. One, in some use cases where you have CPU-intensive applications, I believe that you will see tangible performance gains. But in addition to that, JIT opens the door to additional types of use cases for PHP to be used in. Things like number crunching and other types of CPU-intensive applications where PHP today is just not applicable. It's too slow compared to alternatives. In PHP 8, it will become a very viable contender, and you'll be able to use your language of choice for these purposes as well. In addition, something that we haven't decided yet whether or not we're going to do, but we're thinking about it, is it's going to allow us to implement parts of PHP in PHP. And let's stop on that for a moment. Today, if you want to develop an internal function that's built into PHP, you have to use C. And that has two major disadvantages. One, the skill set required is not a skill set that most of the people in the PHP community have. As a PHP developer, you're not a C developer as well. There are some exceptions, but for the most part, that's true. And secondly, in C development is a lot more complicated and pretty much by definition less secure than PHP development, mainly because in C, memory management is something that you have to handle, and it's quite complicated, and it's very easy to bump into problems like buffer overflows and heap overflows and underflows and all sorts of things that in the PHP space you just don't have to worry about at all. And if we enable developers to implement internal functions in pure PHP, then we're broadening the ability of developers to contribute to PHP itself, and we can also actually make certain pieces of code a lot more secure than they are today, because they're no longer going to be implemented in C, they're going to be implemented in PHP, and thanks to JIT, it's going to be as fast as the C counterparts. So that's in a nutshell the story of JIT. Coming to PHP 8, probably towards the end of 2020, but remains to be seen. Another thing that is coming into PHP 8 is called FFI. It stands for Foreign Function Interface. Foreign Function Interface is the ability to utilize native code libraries. So libraries written in C or C++, directly from PHP without having to write an extension. So if you remember 15 minutes ago, I talked about how PHP 3 was one of the key improvements, or the key features were the fact that it was extensible and made it possible to write extensions, which was a lot easier compared to the situation in its predecessor. In PHP 8, you'll be able to tap into native code libraries without having to write an extension. You'll be able to directly invoke functions and classes in these libraries without having to have C knowledge, or at least have a lot less C knowledge compared to what you need today. It doesn't replace extensions. If you want something to be kind of really nicely supported with an API that is following the PHP way of things, then you would still want to have an extension. For things that are really commonly used, you will likely still want to create an extension. But if you want to utilize a native code library, and today there's no extension for it, and today you essentially have two options. Either you write an extension, which in most cases is not really an option, or you end up having to use some other language. In PHP 8, you will have the ability to directly invoke these libraries without having to write C code, just by importing them in a fairly simple process. So you'll be able to tap into all sorts of things. These are just some examples of things like big data, artificial intelligence, and so on. In PHP 8, they're going to be a lot more accessible, and I view it as something that's complementary to JIT. Again, broadening the horizons of the types of use cases that PHP is useful for. The second part of the keynote, I want to touch on the evolution of the architecture, not of the internals of PHP, which we kind of touched so far, but how PHP fits into the bigger picture. Not the huge picture. I'm not going to talk about things like containers or cloud, but really the vicinity of PHP, specifically the web server. So here too, I'm going to start in the beginning. Going 25 years into the past, PHP was CGI. So PHP as a CGI, it had like all the features of PHP today, but it was really slow. The reason was simple. You had a web server that had to invoke a brand new process of PHP for every request. So a request was coming in, the web server would determine that it needs to be executed by PHP. It would start a new process, an external process, handle it, the PHP file that needed to be executed, and PHP would execute it, return the result, and terminate. And then on every request, on every subsequent request, the exact same process would happen. Now, you don't need to be a performance expert to realize that this is really slow, especially since the cost associated with invoking processes on all operating systems, even more so in Windows, but even on Linux, it's fairly expensive. So this was great functionality-wise, perfect isolation between requests, but it was dead slow. So very quickly, we evolved to this model, which was probably the most popular model for deploying PHP for most of the last 20 years, probably the following 12, 15 years after CGI went out of fame. And with a plugin module, as the name implies, PHP plugs directly into the web server. It loads into the web server, becomes an integrated part of the web server. And then when the web server needs to invoke PHP, it's really a matter of a function call. It's really fast. It's really an integrated part of the web server for all practical purposes. And it was a pretty good architecture, and it's still very common today because it's fast and it does the job. It has pretty good isolation, not quite as perfect as CGI, but for like 1% less isolation, you're getting, 100 times better performance in many cases. So it was a good trade-off. But even that architecture started to show signs of age, and it had two main disadvantages. perhaps more, but two really bad ones. One is that it was, in practice, very much web server specific. We had web server plugins for Apache as well as other web servers, but for virtually all other web servers, it wasn't really good. It wasn't completely stable. It required thread safety in most cases. So in practice, it was an Apache specific. For practical purposes, I'm not talking about an academic discussion, but for practical purposes, this was an Apache specific architecture. And as more and more other web servers became popular, this became a growing disadvantage. The other disadvantage is not quite as apparent, but the fact that you had an instance of PHP built into every instance of a web server was also a disadvantage. You can see that there are like 3 rectangles there, and that symbolizes that there's more than one web server instance. In practice, when you're running Apache, you would have dozens or hundreds and sometimes even thousands of different instances of Apache running at the same time. And with that architecture, you also had an instance of PHP built into every one of them, which was actually quite inefficient, especially in terms of memory utilization. And as the workloads grew and the number of Apache processes on single machines would also grow, this became a very notable disadvantage, which I have to admit at the beginning, 15, 20 years ago, we didn't even think about. But it was, in fact, a disadvantage. And that was the next step in the evolution of deployment architecture for PHP, which I think was triggered primarily by Nginx. It was a necessity, because a web server plugin was not really practical with Nginx. But after it was implemented, we figured that it's actually better, for all practical purposes, to use this model also for other web servers, including Apache. The main reason, okay, before I go to the reason, what do we actually have here? So we have the web server, and we have a separate pool of processes which are running external to the web server. But unlike CGI, we're not invoking a new process every time there's a request coming in. Instead, we have a pool of processes that are waiting for requests to come in. When a PHP request comes into the web server, if it's a PHP request, it will funnel it to the one of the idle processes that are available. The PHP process would execute it, return the result, and clean itself up and be ready for the next request. So in practice, sometimes people think that the fact that it's external would slow things down. In practice, Unix and all modern operating systems deals with inter-process communications very efficiently, so it's actually not slower than having the web server as a built-in part of having PHP. So it's actually not slower than having PHP as an internal part of the web server. And it has the advantage that we're breaking the one-to-one mapping between the number of web server instances for concurrency and the number of PHP instances. In practice, the number of PHP instances can be a lot smaller than the number of web server instances. Web server can be measured in the hundreds or even thousands, and PHP instances can be measured in dozens. Generally, you don't need to have more PHP instances than you have cores or with hyper-threading, hyper-threaded cores on your chip. So anywhere between a handful to maybe a few dozen processes would do the job. This saves a lot of memory and is overall, in most cases, faster than the plugin module, and it's a lot more compatible. It's not more portable to different web servers compared to the web server module that we've seen before. But even that architecture has its limits. And these show especially when we deal with things like microservices. How many of you are actually developing or deploying or maintaining microservices at all? Okay, so not too many. It's still an emerging paradigm. But basic microservices, as the name implies, are services that are really, really small. And microservices change some of the fundamental assumptions that we had, not just us, but all of the folks developing platforms for the execution of web workloads. it changes some of the fundamental assumptions. Perhaps the key fundamental assumption that it changes is that the amount of time it takes to bootstrap the language and the application itself is negligible compared to the runtime of the request. So in the past, you would have a fairly thick request that would take, I don't know, 200, 300 milliseconds to run. An initialization time of the language and even of the app, which would take 10, 20 milliseconds, was no big deal. It was less than 10% of the overall runtime. It was pretty much negligible. When you deal with microservices, the runtime is typically not 2, 3, 500 milliseconds, but it's very often 10 milliseconds or 20 milliseconds. It's really, really short. And then an initialization time of 10, 20 milliseconds, suddenly it takes roughly the same amount of time of the actual runtime. So suddenly it takes something like 100 or 50% or 30% or a very substantial amount of the time of the overall execution runtime. And in order to solve that, it wasn't, let's put it this way, it wasn't really possible to truly solve that while sticking with PHP as we know it. In order to solve that, we had to do something different. And this different thing, it's not something we invented, that's actually something that has existed for a long while, and that is asynchronous execution. It's a bit of a complex. How many of you have used asynchronous execution in any language? Okay, that's a fair number, but still the majority of you haven't. It's not surprising. It's not very common in PHP. It's available in PHP, but it's not very commonly used. It's extremely commonly used in the JavaScript world. Node.js is completely based on asynchronous execution. And I'm going to show you the architecture. It's really simple. And Node.js, for that matter, is exactly the same thing. Instead of async PHP, we write async JavaScript. The way it works, in a nutshell, the main thing that you can notice here is that there is no web server. Not here, not there. It's not inside a web server. It's not next to the web server. There is no web server because PHP itself, in this case, or if it's Node, then Node, they are the web server. They're listening on the socket. They're listening on port 80 or whatever, and they are communicating in HTTP with the remote clients, with the browsers or whatever clients they are. And everything, all of the execution and all of the concurrency are implemented inside PHP itself. And how can a non-multi-threaded language runtime, which PHP is, it's not a multi-threaded language runtime, and by the way, JavaScript isn't either, how can they handle more than one request at a time? At a very high level, if you've never learned about asynchronous execution, that I don't expect this to make a lot of sense, but maybe it's going to be a start and you can learn more about it afterwards. In a nutshell, whenever a request needs to get something over I/O, like waiting for the database to bring back information, or the file system, or a socket, if you're connecting to like a remote web service or something, whenever it's waiting for I/O, instead of waiting, instead of pausing, it actually returns control to, in this case, to the language, and the language can then execute something else. And whenever this I/O is available, when finally the database returns the, what you've queried it for, or the socket has data available, or so on, whenever that happens, we go back to the piece of code that was waiting on it, and we wake it up. It's complex. I don't pretend that it's not, but that's in a nutshell what asynchronous execution is. And the most important part of it is that with asynchronous execution, most of the initialization overhead, both of PHP itself and your app, don't happen on every request. They happen once in the beginning. PHP initializes itself, all of the different data structures, symbol tables, and so on. Your app initializes itself, so you're loading all the different classes, potentially populate all sorts of standard registries and global structures or whatever your application needs. You do that once, and from that point onwards, the PHP process is, you can call it, it's hot, it's now ready to execute, and every subsequent request that comes in doesn't have to wait for almost any initialization overhead. And that is why this model is very, very suitable for microservices, because the initialization time can be trimmed from hundreds of milliseconds to just tens of milliseconds. And as we mentioned a few minutes ago, this is really key when dealing with performance of microservices. An important thing to understand is that moving this architecture, it's not like moving between these architectures, in which it was more of a kind of changing your deployment, changing your installation, but the code pretty much remained the same. Here, you need to change your code, and in my opinion, opinions vary, but in my opinion, in ways which are not always very intuitive. It's difficult to get it right. But for the right use cases, if you do use microservices or intend to in the future, definitely look at it. It's worth it, because the performance is orders of magnitude better. And when I say orders of magnitude, I really mean it. It can be 10, 50, 100 times faster compared to a regular Nginx with FPM. If you want to learn more about asynchronous PHP, there are several different projects for it, like React and Swole. I would recommend taking a look at Swole. Swole is an implementation of asynchronous execution for PHP. That's the way it's spelled. And specifically, if you Google for Expressive and Swole, let's see if I can do it for you. Yeah, if you Google for, let me show the whole thing, Swole, Expressive, and the how it works part, ignore the caution, it's not right. It gives you kind of a very simple intro, or very basic intro, I should say, into how this works on top of a micro framework called Expressive. And you can learn more about it using that. Now, if you're not into, kind of as a bonus, if you're not into changing your code completely and moving into synchronous PHP, which I think for most of you is probably the right choice, not to move, there's still a way to get some of the benefits of asynchronous PHP if you migrate to PHP 7.4. It's a small subset, but in PHP 7.4 we implemented something that gives you a part of the advantages that you would otherwise get in asynchronous PHP, specifically the ability to preload files into memory. In PHP 7.4 you can instruct the language to preload a set of files into memory, and these files are going to be available for any request that comes in, whether or not you explicitly load them. What it does, it actually allows some of the overhead associated with fetching, with loading files, or even fetching them from the op cache. It allows this overhead to be eliminated. Specifically, things like dependency resolution and matching inheritance of classes, things like that. I know that many of you think that everything is the op cache, so what's the big deal to load it? It's coming from memory. That's true, but still, when a file is being fetched from op cache, it still has some overhead. Again, primarily on things like resolving dependencies between classes and inheritance and things like that. So if you upgrade to PHP 7.4 and you have a web server that is serving one application, it's not really suitable for a web server that serves all sorts of different applications that may bump into each other. But if it's serving just one application, then you can fairly easily, with minimal effort, typically in many cases without having to change your code at all other than implement this, you can realize a performance gain of up to roughly twice as fast, better performance compared to without it. Not quite as exciting as the performance gain you would get from moving to asynchronous PHP and on top of microservices, but still, this is a lot more applicable than this is applicable to a lot more use cases than async PHP. So with that, I'd like to thank you. Thank you very much. And I think I was off by 10 seconds, but we don't have time for questions. But if you do have questions, I'll be happy to take them. I'm here all day. Thank you very much.